Ever get that feeling? Like you're just kind of skating on the surface of things, especially with tech. I mean, it's like there's this whole crazy, intricate world going on behind the scenes, but we only see bits and pieces of it.
Totally. And that's exactly what we're digging into today. The nuts and bolts, the real core mechanisms that make computers tick. And you know what? It's more connected to everyday life than you might think.
Yeah, it's like a deep dive right into algorithms and how they work and the math behind it all. We've got some really cool materials here to make this stuff crystal clear, practical. So we're cutting through the confusion and getting to that core logic of the digital world.
It's about understanding those step-by-step instructions and calculations that make everything happen.
Right, we're going to break down how algorithms operate. They're like these ordered sequences of actions. And then we'll see how they use math to actually get things done. So we're talking sequencing, like the order things happen in. Selection, choosing between different things based on what's going on, and iteration, like repeating steps over and over.
It's everywhere, really. Think about it like following a recipe. The order you add ingredients matters. You decide to add a certain spice based on, what you like, and sometimes you have to keep stirring until, the batter is just right. That's algorithms in action, all around us.
Okay, so let's start with algorithms themselves. What exactly are they?
Well, at their most basic, an algorithm is basically a set of instructions, a series of steps you follow to complete a task. It's finite, though, meaning it ends. And when you do it right, when you follow the steps in order, you get the result you're looking for.
It's interesting because we see algorithms all the time in our daily lives, even when we don't realize it. It's like anytime you follow steps to get something done, our sources mentioned baking, and that's a great example. You've got your wet ingredients, your dry ingredients, and you bake it at a specific temperature for a specific time. And if you mess with the order of those steps,
you're not going to get that perfect cake. And even, think about it, your morning routine is like an algorithm. You probably do things in a certain order, maybe shower, brush your teeth, get dressed.
Right, you've got that sequence down. So you mentioned the 3 core concepts behind algorithms. Let's start with sequencing.
Sequencing is pretty straightforward. It's all about the order. Each step leads to the next, just like in that baking example.
Right, you wouldn't ice a cake before it's baked and cooled. Right, order matters. And it's not just about doing things in order, like the efficiency of the order, how good it is, can really change how fast or how well an algorithm works, especially when you have tons of data.
That's a really important point. And then you've got selection, which is our second core concept, but this is where the algorithm has to make a choice, a decision.
It's like a fork in the road.
Yeah, exactly. The algorithm looks at a condition, asks a question, and based on the answer, true or false, it picks which way to go. The example in the source material about the umbrella, I thought that was perfect. The algorithm checks the weather, is it raining? And then it decides, okay, grab the umbrella, or nope, leave it at home.
So if the condition is met, do this. If not, do that. Cool. Okay, and the third piece, iteration.
Iteration is all about repetition. You keep doing the same steps over and over as long as a certain condition is true, like the homework example in the source. You have a bunch of problems to solve, and you do the same thing for each one. Read it, solve it next, until you're done with all of them.
So you're looping back, doing the same actions until you reach the goal.
Exactly.
So these algorithms, these instructions, how do we actually represent them so people can understand and use them? I mean, you can't just have them floating around in your head.
Right. Our sources talked about 2 main ways, flowcharts and pseudocode. And it's interesting how each of those gives us a different perspective on how the algorithm is structured and its logic. Flowcharts, they use visuals like diagrams and arrows to show the steps and their sequence. Decisions, those selection points, they're usually shown as diamonds. In loops, they use arrows that circle back to show the iteration. Remember that example, counting even numbers in a list. The arrows show the sequence, the diamond asks, is it even? That's your selection. And then the loop going back to get the next number, that's the iteration. Of course, when things get more complex, flowcharts can get pretty crazy looking. Subroutines, parallel processes, they've got symbols for all that.
Yeah, I can see how those visuals would make things click for some people. And then there's pseudocode, which I like how the source described it's like almost code, simplified. You're using a mix of regular language and some keywords that look like code to describe what the algorithm is doing. More specific than just plain English, but not as strict as actual programming languages like Python or Java.
Exactly. Pseudocode helps us be really clear about the logic without ambiguity. Remember that example? Finding the biggest number in a list of positive numbers. You had clear steps like 1. Initialize a variable called largest to 0. 2. For each number in the list. 3. If the current number is greater than largest, then update largest to the current number, and you repeat step 2 until you've checked all the numbers. That's the iteration. You could practically translate that pseudocode directly into actual code.
Like that if statement would probably become an actual if keyword in a lot of programming language.
Exactly.
Cool. Okay, so we've got sequencing, selection, iteration, the basic building blocks of algorithms. We've seen how flowcharts and pseudocode help us lay them out. Now let's talk about how these algorithms actually produce results.
Yeah.
What role does math play in all of this?
Right, the math. And our source pointed out how important sequencing is here in code segments when you're evaluating mathematical expressions.
It's amazing how even simple lines of code can actually involve these math expressions. And because of sequencing, the order they're executed in is critical, because each line might involve calculating something.
Absolutely.
And these expressions can be made up of different things. The source mentioned direct values, which are stored in variables. Think of them like containers that hold information. We have the value of one variable being assigned to another variable, and also the result of a math operation. And even the outcome of calling another piece of code, a procedure.
Right, so think of a variable like a labeled box holding a piece of data. And an expression, it's any combination of values, variables, operators, and function calls that. When you put it all together, gives you a single value.
Okay, so you could have a simple assignment like age equals 30. The expression there is just the number 30, and it's being stored in the age variable.
Exactly. Or you could copy what's in one container to another, like previous score or current score. The expression there is whatever value is currently in the current score variable.
Right, and then you have actual calculations like total cost equals price plus tax. The plus sign there, that's an operator. It adds the value stored in the price and tax variables. And the result, the sum, is stored in the total cost variable.
And don't forget, like the source mentions, sometimes expressions involve calling another piece of code, like a procedure or function, like average, calculate average grades. That calculate average part, it would do some math on the grades data and return a single value, which is then stored in the average variable. The main point is, every expression, no matter how complicated it looks, it boils down to a single value that gets stored somewhere, usually in a variable. Oh, and this is where data types come into play, although the source didn't really get into that. What kind of data a variable holds, like a number or text, can affect how these operations actually work.
Right. And because of sequencing, the order these expressions are evaluated in a block of code is super important, right? The computer goes line by line from top to bottom.
It's critical. The order really determines what the final values in those variables will be. Remember that example from the source. First, grade 1 gets a value, then grade 2 is assigned the current value of grade 1, and then average grade is calculated using whatever values grade 1 and grade 2 have at that moment. Change the order, and the final average grade might be totally different.
Yeah, got it. Okay, let's do a practical example. Our source gave us a little piece of code. We can walk through it step by step. It starts with num1 equals 2, num2 is 4, and num3 equals 6. So what happens next?
Okay, so those first 3 lines, those are direct assignments. Num1 is now 2, num2 is 4, num3 is 6, and the next line is num1 equals num2 plus num3. You always evaluate the right side of the equal sign first. Num2 plus num3, that's 4 plus 6, which is 10. And then that result, that 10, gets assigned to num1, overriding whatever was there before. So now num1 is 10.
Okay, makes sense. The next line is num3 equals num1 plus 5. What happens there?
So now num1 is 10 from the previous step. So num1 plus 5 is 10 plus 5, that's 15. And that 15 gets assigned to num3. So num3 is now 15.
Got it. And then we have num2 equals num1 plus num3, 5. Okay, few things going on here. What's the order of operations?
This is where that standard math order of operations comes in. In most programming languages, division happens before addition. So you do num3, 5 first. Num3 is currently 15, so 15 divided by 5 is 3. And then you add that result, the 3, to the current value of num1, which is 10. 10 plus 3 equals 13. And that final value, the 13, is stored in num2. So num2 is no longer 4, it's 13.
Okay, cool. And then the code would display the current values of num1, num2, and num3. So based on what we just did, what would those values be?
We found that num1 ends up as 10, num2 is 13, and num3 is 15. This is a good example of how the order those lines are executed, and the order of operations within each line determines the final result. Even changing the order of those simple assignments would probably give you different final values.
Absolutely. Now, our source talked about some common arithmetic operators that we see in these expressions. Addition, subtraction, multiplication, division. We're all familiar with those, but they also brought up modulus. Can you break down exactly what that one does?
Yeah, the modulus operator. It's represented by the percent sign, percent, or sometimes the keyword mod, and it's pretty handy. Regular division gives you the quotient. Modulus gives you the remainder after you divide two integers. The sorts had a good analogy about sharing candy. Say you have 9 pieces of candy and you want to divide them equally between 2 friends. Each friend gets 4 pieces, right? But there's one leftover. That leftover piece, the remainder, that's what 9 mod 2 gives you. 9 mod 2 equals 1.
Oh, I like that analogy. So if you had 9 candies and 3 friends, 9 mod 3 would be 0 because it divides evenly, no remainder.
Exactly. Modulus is really useful for things like figuring out if a number is even or odd. If you do number mod 2, you get 0 if it's even, 1 if it's odd, or for making things loop around like days of the week.
Okay, so we have all these different arithmetic operators, but how do they all work together when they're in the same expression? Our source reminded us about the order of operations.
Yeah, that order is super important to get the right answer, especially when you have a lot of operators. It's like a hierarchy, decides which operations happen first. You might remember PEMDAS, parentheses, exponents, multiplication and division, addition and subtraction, or BODIME, brackets, orders, division and multiplication, addition and subtraction, same idea.
Okay, so anything inside parentheses or brackets, that goes first. Then exponents or orders. Then multiplication and division, going from left to right. And finally, addition and subtraction, also from left to right.
Yep, that's the order. And the source had some good numerical examples to show this. Like, if you have 10 plus 5, 8, 4, the multiplication happens first, 5 times 8 is 40. Then you do the division, 40 divided by 4 is 10. And finally, the addition, 10 plus 10, so the answer is 20.
But if you added parentheses, like 10 plus 5, 8, 4, now the addition inside the parentheses goes first. So 10 plus 5 is 15. Then you do the multiplication. 15 times 8 is 120. And then finally, the division, 120 divided by 4 is 30. See? Just adding parentheses changes the whole thing.
It does. And that example with parentheses around the division, 10 plus 5, 8, 4, you do what's inside first. 8 divided by 4 is 2, then the multiplication, 5 times 2 is 10, and finally the addition, 10 plus 10, which is 20. So the parentheses give you control over the order of the calculations.
Got it. Let's do one that's a little more challenging with variables and that modulus operator. Our source gave us this. Result is num1 4 num3 plus 9 mod 2 num3. And we know that num1 is 12, num2 is 25, and num3 is 14. Can you break it down step by step?
Okay, let's do it. First, division and multiplication have higher priority than addition and subtraction, and we go from left to right. So we start with num1 4. Num1 is 12, so that's 12 divided by 4, which is 3. Next, we have 3 num3, and num3 is 14, so that's 3 times 14, which is 42. Now, for the modulus 9 mod 2, the remainder when you divide 9 by 2 is 1. So now we have 42 plus 1 num3. And finally, addition and subtraction from left to right. 42 plus 1 is 43, and then 43 minus num3, which is 14, gives us 29. So the value that would be stored in result is 29.
Okay, so you really have to pay attention to those rules to get the right answer. Our source gave us one last code segment to practice with. It goes like this. Num1 equals 40, then num2 equals num1 2, then num3 equals 5, num2 plus 3, and finally result equals num2 mod 3, num1 plus 4, num3 2. Let's work through this one together and see what that final result value would be.
Sounds good. So first, num1 is assigned the value 40. Then num2 gets the result of num1 2, which is 40 divided by 2, that's 20. Next, num3 gets the result of 5 num2 plus 3. 5 times 20 is 100, plus 3 is 103. So num3 now holds the value 103. Now let's break down that last expression to get result. Num2 mod 3, num1 plus 4, num3 2.
Okay, step by step using the order of operations. First, we've got num2 mod 3. Num2 is currently 20. So what's 20 mod 3?
When you divide 20 by 3, you get 6 with a remainder of 2. So num2 mod 3 equals 2.
Right. Next up is multiplication and division from left to right. We have 2 num1. Num1 is 40, so that's 2 times 40, which is 80. We also have num3 2, and num3 is 103. So 103 divided by 2 is 51.5.
Right, so now our expression looks like result equals 80 plus 4, 51.5. Lastly, we do the addition and subtraction going from left to right.
Okay, so 80 plus 4 is 84, and then 84 minus 51.5 gives us 32.5. So the final value of result will be 32.5.
Exactly. This example really ties everything together. The step-by-step instructions, using variables to store values, applying those arithmetic operators, and how crucial that order of operations is to get the right answer.
So to wrap things up, we looked at how algorithms give us this structured way to solve problems, step by step. And that sequencing, the order of those steps, is super important. Then we dug into how math expressions within those algorithms actually manipulate data and give us results. And we really emphasize how important it is to understand and use the right order of operations when figuring out those expressions.
Yes. Understanding these core concepts, how algorithms flow logically and how those math expressions are evaluated precisely, gives you a powerful lens to see not just how computers work, but the logic behind a lot of things we do every day. It's the foundation of all software and digital technology.
So here's a thought to take with you. Now that you have this deeper understanding of how computers follow those instructions and carefully evaluate those math expressions, think about other things you do in your life, even outside of tech. What other tasks can you break down into steps, decision points, and repeated actions? You might be surprised how much math thinking, even subtly, is already a part of your routine without you realizing it.
It's about recognizing the inherent logic and structure that's all around us. We really encourage you to think about this some more. Maybe you look for more examples of algorithms and math expressions in action, both in the digital world and in the real world.
Hopefully, our deep dive today cleared up some of the mystery surrounding these fundamental ideas and gave you a better understanding of the technology that shapes our lives. Thanks for joining us on the Deep Dive.